Hi everyone, my name is Piotr. I'm a distributed systems engineer turned AI engineer. I've been working on ScyllaDB and Torso for a few years, and meanwhile I also co-authored two books, and then ultimately I joined Poolside to work on large language models. You can find the database performance book online for free. Give it a try, it's nice. Just to clarify, I'm not really an AI programmer. I usually don't understand the industry acronyms, and even when I look them up, I immediately forget them. I need to look them up again in a few minutes. Anything AI related in this presentation, so pretty much the whole presentation, should be taken with a grain of salt. Back in the days, I first heard about artificial intelligence. It was usually referred to as machine learning, the old term. Half of it was about finding paths in a graph with animal-themed algorithm names like ants, bees, and other bugs. And the other half was exploring how neural networks work. I mostly heard that it's very nice for predicting something of proteins in bioinformatics, and also quite great for writing bots for card games and video games and so on. Things obviously changed a lot in the last few years. The paper "Attention is all you need" kickstarted a revolution. Everybody doubled down on large language models, and then suddenly everybody started using ChatGPT for everything. And then 37 more companies and whole countries joined the arms race. Graphics processing units don't really process graphics anymore and are instead used to train models and infer data from them because they turned out to be very good at efficiently multiplying matrices. From my perspective, it happened really fast. Suddenly a new huge industry appeared out of nowhere. Technically, the research had been, of course, going on for decades, but nobody really treated it seriously enough until recently. At least nobody I know in my personal bubble of AI ignorance. Large language models need lots of data. For instance, the whole internet to be smarter. The whole internet is a very general term, but regardless of the exact definition, it's lots of data that needs to be stored, served, queried in a structured way or an unstructured way and processed. All that is a perfect job for distributed systems because in order to process and pack the whole internet for training in an efficient way, it needs to be done with high parallelism, right? Those of retries, deduplication, replication, security, and so on. Joining an AI company was a little bit of a cultural shock for me. To alleviate the same cultural shock for you, I assembled a short list of things I needed to acknowledge and slowly process before I felt comfortable speaking to colleagues about technical topics, although I still really don't. One is tokenization. Nobody ever means splitting source code into tokens before parsing, as compilers do. Now it's mostly about encoding text with numbers by trying to efficiently assign those numbers to substrings to achieve a dictionary of a given size. To make it more confusing, this dictionary is often called a model, which is not to be confused with a large language model, totally different things. It's not clear how many bytes a token is because they are variable size, and yet everybody uses tokens for measuring all kinds of sizes. If you assume a token is around 4 bytes, you will usually not be orders of magnitude wrong, so that's what I do. The state-of-the-art approach to tokenizers changes daily, so maybe my estimate is already not up to date. Always do your own research first. And also, as a distributed systems person, I automatically read RW as read-write. It is not the case for RWKV, which the authors intend to pronounce as Rakov or some similar guttural sound. Just keep it in mind, it's an approach to neural networks, nothing to do with storing data. And as I mentioned before, half of the things in the industry is called model, and the other half is called context. At first, I suggest you just smile and nod when somebody mentions any of those two. And in time, you'll just start getting vague intuition over the meaning of any of those. Let's talk about something I do know things about, latency. It's an important measure in distributed systems because it says how long users or components have to wait until they observe an effect of their requests. You send a database query, and the time you spend getting annoyed it's not done yet is latency. It's also part of a very neat and useful equation, Little's law. The original wording is impossible to remember because it goes on about long-term average number of customers in a stationary system. Don't ask me what a stationary system is, I don't know. The compressed and simplified meaning is that concurrency equals throughput times latency. That simple rule is great for tuning your distributed systems because at some point you can observe that making more concurrent requests to your system does not increase the amount of work you can do, and it just makes you wait longer for individual results. In other words, if you reach max throughput of your system, for instance, your internet wouldn't squeeze any more data through the wire, then it's clear from the equation that when W is constant, increasing concurrency just increases latency too. There's going to be a whole book dedicated to latency available soon, and I bet Pekka has lots of rants ready to publish on why dealing with latency sensitive systems is a real pain. The biggest mind shift I had to go through after joining the AI race is that nobody really cares that much about latency anymore. Training large language models is a typical batch workload, and it's important to process all the data as soon as possible. It is, however, not usually that important if a single particular request took 100 or 500 milliseconds. Inference time is a different matter. This is where end users wait for the model to respond. And normally, we as an industry would try really, really hard to make it fast. But we don't have to because of a brilliant social engineering maneuver that OpenAI pulled on the whole humanity pretty much. Namely, they let the users stare at the partial responses that the model spits out because it kind of looks like a human would reply to you real time. Absolutely brilliant because it just employs human nature. You'd get furious after looking at this spinning wheel that says please wait after 3, maybe 5 seconds tops, and assume that something hung and you need to turn it off and on again. And at the same time, when a large language model meticulously produces the whole response in 2 or 3 minutes, but lets you see individual letters being typed, you look at it with pure excitement and marvel at our superior AI technology. Don't get me wrong, it's still important, especially cost-wise, to make inference fast and efficient, but the human factor here, at least, is bypassed. Throughput is kind of the counterpart of latency in Little's law, and it's the amount of data you can squeeze through your system in given time. As mentioned before, when training models on vast amounts of data, throughput is usually the metrics we're interested in. It defines if we'll be able to finish a training run today, this week, or this decade. And as long as all the pieces of the distributed system are still functional, it's usually better to sacrifice latency of a single request for increasing total throughput. Peak throughput, maximum of what the system can reach, is typically called bandwidth. Again, reminder, once you reach your bandwidth, no real point in increasing concurrency, or you'll just increase latency. That's the mind shift I was talking about. With databases, you have to be careful to satisfy both the analytical people and the point query people, balancing between batch and online workloads. Some users need low latency, other users insist on high throughput, no matter the cost. In artificial intelligence use cases, you can just assume high throughput and high latency over low throughput and low latency. If you can achieve high throughput with low latency, great, but definitely not at all costs. Typically, instead of measuring throughput, engineers should look at goodput. This portmanteau just means useful data processed by the system as opposed to just data. It's important because one can reach peak throughput by sending duplicate or meaningless data or logs, retries, errors, and so on. And it doesn't really make the system any more useful or efficient. Interestingly, a right small dose of redundant data can be quite beneficial to your training. Not an AI engineer, so I won't pretend to understand the details, but my simplified understanding is that it helps the model reason better if it also sees some inaccuracies. And that's because humans later querying the system will also provide those inaccuracies in their prompts. Let's try and estimate what's the scale of data used in handling and training large language models. First, let's define again what tokens are. Basically, they are just strings of unspecified length with a number assigned to them. That's not the only approach, but the popular one. If you're familiar with how dictionary-based compression like LZ4 works, it's a little similar in some sense. It's not possible to directly translate tokens to bytes, as the former have variable length, but again, if you assume 4, you won't be wrong by orders of magnitude. So how many tokens of data are we talking about worldwide? Wikipedia articles have a few billion. So do Stack Overflow responses. And as for code repositories, GitHub, GitLab, and Bitbucket combined have a few trillion. This data can be categorized in many different ways, but one important distinction is if it was produced by humans. Books, papers, internet forums, repositories, especially from a few years back, are mostly natural, organic, gluten-free, no preservatives. The quality of this data still varies a lot. Some books are great, some are terrible, and same goes for academic papers and virtually everything else, except Hacker News comment section, which has a very high density of experts in all industries, happy to tell you why you're wrong and that the right answer is actually to use Postgres. This natural data is the original data set that the first language models were trained on, and I see it as a seed data set for the whole AI revolution. Synthetic data suggests that it's data that is just made up, but there's a little more to it, actually much more to it. Lots of people may assume that synthetic data boils down to asking the models questions and collecting answers, but that doesn't really provide any more information. If anything, it would just make the model more presumptuous, having been taught its own outputs as ground truth. Models can, of course, learn from each other, but that's also just creatively borrowing other people's data and training on it. If you don't want to be accused of stealing, you can just call it distillation, which is an academic word for the same thing. Real value from synthetic data is that we can produce it in a meaningful way by actually adding some information. Think analyzing the grammar of all Wikipedia articles and showing the model both the original and the fixed versions, or giving the model not only source code repositories but also outputs of this code when it's actually executed. Then, of course, the final category is just the made-up stuff, because the right dose of it can somehow make the models smarter too, or maybe just more human-like. Internet has lots of data, but this data is not exactly high quality. Fortunately, there are ways both to measure the quality of that data and to remove the redundancies. If you take all GitHub open source repositories as is, it's trillions of tokens, but how many of those are just forks with seven lines changed total in them? It's a surprisingly high amount, believe me. And more often than not, the code also stopped compiling after the last change and it was dished forever. So it's not really very smart or useful data anymore. Creative did application trying to reduce a large set to unique enough elements while also using the highest quality elements as representatives is not easy. But there are whole books on the topic, mentioning clever approaches like mean hashing, Bloom filters, hyperlog, and other brilliant algorithms that help a lot to get your data sets in a decent shape. Those algorithms are often highly concurrent too, which makes them, again, a perfect fit for large-scale distributed systems. Now let's discuss how AI people store their data. Data lake was introduced as a term for information kept in almost unstructured form. A more representative name would be data mess or maybe data landfill, but I suppose lake has better connotations. The access pattern for adding data into the data lake is to just add everything as is and figure out accessing it later. The access pattern is therefore tricky, since the data is inherently not very much structured, so the only operation that you are really guaranteed to succeed is take the data in the form it was previously inserted. In some cases, you can try full search or maybe some kind of grouping, indexing, and so on, but anyone trying to fetch useful information from a data lake would probably agree that it's almost hopeless. Then people fortunately realized that data lakes are great to gather data, but are a huge pain when trying to operate on it. So they invented both another word for it and another approach. It's called data lakehouse, and it's apparently a combination of lake and warehouse, as in data warehouse. And what it allows you to do is still accept barely structured data as input, but then have a systematic way of querying it, for instance, with good old SQL. The most prominent example of a data lakehouse architecture is Apache Iceberg, to the point where I'm not even aware of any other implementations of the idea. With a structured way of querying the data, while also being able to just store it relatively cheaply in any kind of object store, which in practice just means S3. It took over the whole data market, and it's safe to assume the whole world uses it for large enough data sets in one way or the other. We have the data, now how do we process it? You can of course do it directly by writing programs that take data as input and spit out processed data as output, but sooner or later you end up having a framework for defining what needs to be done and when. Then you can define replication to make sure you're resilient to losing data, retry in case a job fails, not retry if the job fails but it's not idempotent, that we can't risk duplicating the outputs. Make sure we only compute as much as needed without burning through too much CPU. Make sure we always compute on fresh data, not some outdated data sets, and so on and so forth. There are many projects out there to give you an orchestrator for jobs like that. One nice example is Dagster. It's open source. And as the name suggests, its core idea is to store a directed acyclic graph, DAG, of assets, and making sure that you can materialize those assets in an efficient and safe way. A while ago, there was a clear boom of vector databases. People realized that in order to store embeddings, that is, vectors of numbers, and then also run various approximate nearest neighbor search algorithms on it, you have to have a specialized piece of software to get the job done efficiently. Looking for nearest neighbors is important for getting related documents out of your database, for instance, to improve the context of your large language model prompt. Thing is, it turned out that users don't want to just store and retrieve vectors or embeddings. They also want database features they are used to. So SQL support with all kinds of regular rows and columns abstractions, indexes, and so on. And then another approach emerged, or rather, it has already been there all the time. Namely, just your regular database, say Postgres, can just add support for storing vectors and use smart algorithms to search through them. It's usually simply faster and more efficient to add a feature to your existing database than write a database from scratch. I've been there a couple of times now, writing a database from scratch, and it's a little traumatic experience, so best to avoid it. The vector is not inherently a very complicated data structure, and most existing databases can already efficiently represent them with the data types they already support. And adding fancy neighbor search algorithms is something that needs to be done, but then most of the popular databases support extensions, plugins, modules, whatever the name is. And with those, you can simply improve your existing database with new capabilities without forfeiting user experience you're already familiar with. So while I think it still makes sense to experiment with databases specialized just for AI and vector search, it's often better to just stay with the database you have and install an extension or two to see if it works for you. To sum up, I was a little skeptical at first, and I didn't understand why would a distributed person go work in AI, but there obviously is lots of distributed systems work to be done here in the industry, and in retrospect, I think it does make a lot of sense to jump on the hype train. That's it. Thanks.